Hello and welcome to the Oxford Online Maths Club, coming to you live from the University of Oxford. My name's James and today I'm joined by Rebecca.
Hi, I'm Rebecca. I'm a first year at Keble College doing maths.
Hooray. And I've worked out how to start a live stream. You'd think I'd have worked it out by now, but somehow not so much. Great to have you with us if you're watching live. We know it's half term at the moment, so we think people are going to catch up maybe after the live show. If you're here live, you can join us in a live chat, which is over on Vvox. There's a link at the bottom and in the YouTube description, and there's a separate link on the Maths Club homepage. If you haven't seen the Maths Club homepage before, we have a whole website with back episodes and other further reading notes. That's over on /r//club on the Maths website. I'm going to see who's here at the moment. I think I'm joined. Oh, hello. I made a mistake there, but we're good. How are you doing, Rebecca? Are you all right?
Good, thanks. Yeah, pretty good day.
Nice. What sort of maths have you done today?
I've had a very applied maths day today. So I had lectures on dynamics and Fourier series, and then I had a dynamics tutorial. So very applied, very sort of real world.
Very real world, but still in a mathematician sense. I do tutorials for Fourier series, so I'm aware that my students are currently learning the magic of taking a Fourier series of something and solving physical problems like that. So that's good stuff. Oscar's here, so hi Oscar. And somebody else anonymous has said hello, which is a reminder to me that you can be anonymous in chat if you want to. You can sign your messages with your name if you like, but you don't have to. Everyone's welcome here, whether you want to let us know who you are or not. And this is also a reminder to me that Joe is moderating chat today. Hi Joe. I don't know if you're watching the stream, but hi. Gabe's here and Praveen is here as well. Should we do our poll? It's a smaller group today because of the half term. Rebecca, we do this poll sometimes. It's a rating scale thing. How was your day? They're supposed to rate their day on a 1 to 5 scale. There's really not very many people in chat today. Oh, and the people who are here are voting now. How would you say your day was on a scale of 1 to 5?
Ooh, I'm gonna say 4. Yeah, solid
four's
4.
Pretty good. Yeah, okay. I think I'm having a 4. I did some tutorials that my students asked me really tricky questions, which, from your point of view, is what tutorials are for, I suppose. And I answered some of them, but some of the others I had to say I'm not sure. We got some votes for 4 stars, but we've got votes for all the other numbers as well. I'm always keeping an eye out for people in chat who vote in these polls for 1 or 2 stars, who are not having a great day, but for whatever reason have logged into an Oxford Online Maths Club live maths session to see some mathematics. And I sort of hope that seeing some maths is a useful thing in your day. Our average is about 3.5 stars. What is the average? 3.64 to 2 decimal places. Let's make that a little bit wider. That's better. Good. Okay. Thanks for voting in the poll. Let us know in chat what you've been up to in terms of maths today. But I think I'm supposed to hand over to Rebecca. So it's about today's topic. Rebecca, what is today's topic?
So today's topic is geometric inversion, which is essentially a transformation of the plane in the same way that, say, you might reflect in a line, except we don't invert with respect to a line, we invert with respect to a circle, which leads to some interesting maths.
Okay, inverting with respect to a circle. That sounds really good. Okay. Oh, Joey is watching. Hi, Joe. Okay, we're going to do that over here, I think. Okay.
So, I guess just to be able to draw some parallels, let's consider reflection in a line. So, you give me a line L in the plane, and I can perform the reflection in that line. So, I take a point P, and the way I construct its reflection is I drop a perpendicular from P to that line, and then I sort of go the same distance on the other side. I carry the line on, and I get to the image of P, which I'm going to denote by P prime. So hopefully that's kind of fairly standard. I think it's worth noting that points on the left of the line are going to map to points on the right of the line. Points on the right of the line are going to map to points on the left of the line. And then kind of obviously, if you have a point on the line, it's going to stay fixed by that reflection.
Yeah, this is a
So
classic mirror image of points, isn't it?
yeah. So like no surprises there. So inversion. So how do we define inversion with respect to a circle? So you give me a circle, which I'm going to call omega, because I've got a tendency to name circles after Greek letters. And I'm going to let the center of my circle omega be O. So I will sometimes call O the center of inversion, and I'll sometimes call omega the circle of inversion. And I'm going to say that omega has radius r. So now you give me a point P in the plane, and I want to try and construct the image of that point P under inversion. So there's a kind of recipe for doing this, right? So we take our point P, we draw the line OP, and what we're actually drawing is, it's called the ray OP, so it just means like the side of the line that's on the same side of O as P.
Okay. Like a ray of light, I guess. Sorry. Like a ray of light, beaming out from O to P and onwards.
And then we're going to define the image of P under inversion to be this point P prime that lies on this ray and that satisfies OP times OP prime. So that's like the distance OP times the distance OP prime equals R squared. So kind of breaking that down, I guess. Here, P is inside omega. So OP is less than the radius R. So in order to make OP times OP prime equal to R squared, we're going to need OP prime to be bigger than R, right? And so P prime is going to map to some point that's kind of here on that line.
Okay. So it's on the other side of the circle, I suppose.
So yeah, importantly, if you're inside the circle, you end up outside. If you're outside, you end up inside.
Okay. But so it's thematically the same as, it's thematically similar to reflecting in a line, but there's some differences, right? It's not the same distance on each side. You've got this multiplying thing going on.
No, so this kind of, if you look at this point here, and we call that like, I don't know, S, then like PS is not always the same as P prime S. Because this kind of, you've got a multiplication thing going on.
Sure.
And I guess what's also worth mentioning is like, with reflection, we say that reflection is an isometry. It preserves distances between points. So if you have points like A and B and you reflect them both, then the distance between the images, so like A prime and B prime, that's the same as the distance between A and B. But you can sort of see that inversion's not going to have this distance preserving property, because we said that like any point outside the circle goes inside the circle. So like if you take 2 points really, really far apart outside the circle, then they're both going to get mapped inside the circle and be forced closer together. So you're not going to get this same kind of nice preservation of like shape and angle and all these nice things. Well, actually, you do get preservation of angle, but that's a different story.
Okay. So it's mapping everything outside the circle to inside the circle. Everything inside the circle gets kind of turned inside out to outside the circle. So it's not preserving distances because the big distances wouldn't fit inside the circle. Got it. Okay. Somebody in chat says it's a bit like geometric mean. And I guess that's right, that the geometric mean of those distances is the radius of the circle. That's
nice. Yeah. I guess kind of while we're talking about chat, I've got a couple of questions that chat might like to try and answer. So the first one is like, what are the fixed points of inversion? So where can I put P so that when I invert, like P prime is the same as P? Which points map to themselves? I don't know if anyone wants to think about that.
Yeah.
And then a second kind of really pressing question is, does this definition I've given you, is it complete? Is inversion well defined? Or is there some kind of point in the plane for which this recipe I've given you to construct the inverse like fails? Because actually kind of it does fail somewhere, and I'd be interested to see if people can give me some ideas about where.
There's a bit of chat lag due to broadcast and people typing things, which I'm going to use to say hi Zach. Zach's running late, and also to say oh no to the person who said they were having a 1-star day because they're ill. People have now got in chat to tell us. I think they're answering your first question about which points are fixed under the inversion. 3 or 4 anonymous people have said when P's on the circumference of the circle, when it's on the outside of the circle. Keep them coming. Here we go. Yes.
That's perfectly right. Yeah. So the fixed points. Clearly, if you have some point like Q over here, then like if we let Q equal Q prime, then you have like OQ and OQ prime are both R. So you end up with this relation over here being satisfied for Q.
Yeah, which is kind of a bit like how the points on the mirror in your straight line example stayed on the mirror, I guess. And people are now also asking about the centre of the circle. I can see at least two people in chat. Sorry if I missed other people. Said that if P is on O, if P is at the centre of the circle, then you can't do this inversion.
Yeah, I agree. So kind of, you get 2 problems when you try and invert O. So the first thing is, I told you like, you have to draw the line between O and your point. So like I drew OP here, but like this line joining O to O, like what does that even mean? I could draw loads of possible lines. And then secondly, kind of more fundamentally, if you take the relation here of OP times OP prime equals R squared, and you apply that to O, well, you get like OO times O prime equals R squared. But like the distance between O and O is 0. So you get 0 on one side and then R squared, which is positive, on the other side. And like clearly there's nowhere I can put O prime that would satisfy this. So we kind of have a problem. And I guess you could just say, well, let's ignore O. But turns out what the best thing to do mathematically is we're going to define a point somewhere off at infinity. We're going to call it P infinity. And we're just going to say, well, my point O maps to P infinity. Which is a really weird kind of concept. But it turns out to be quite useful. So what we're essentially saying is this transformation inversion is defined on the whole kind of plane that we're used to. But we're also going to extend this plane to include this strange extra point called the point at infinity that we can't see, that we sort of imagine being somewhere infinitely far away in the distance.
Kind of weirdly infinitely far away in the distance in every direction. Because whichever way you go, you'll end up at what you're calling the point at infinity, P infinity. Okay, so I can kind of see how, as a mathematical construct, that's the image of the origin of this reflection. That feels like it should be really far away. Yeah. Not really sure.
And I guess probably we want to say that, like, so to be complete, O maps to the point at infinity. We've now created a problem in like where does the point at infinity map to, and that's quite easy to solve because we say that the point at infinity maps back to O.
Okay.
And it will be useful later for us to think of P infinity as being like a point which lies on every single line in the plane. So like all lines meet infinitely far away at this point, which doesn't make much sense now, but hopefully will make a little bit of sense later.
Okay. Gabe in chat wants to know whether we can invert curves as well as. I guess we've only inverted points so far. You've just given me a point, and I guess you could invert some collection of points. You could flip all of them by inverting each of those points and finding out where they go.
Absolutely.
Is that what we're doing next?
And I think that's where things get exciting.
Okay.
So I guess a quick thing to mention as well is we've got this idea of like when you invert a point P, you get to P prime. But then if you invert P prime, you're going to get back to P because this relationship sort of still holds the other way around. So that's just worth kind of noting before we move on. But yeah, I think it would be nice to look at what happens to some lines and some circles. So I guess sort of the most fundamental kind of sets of points that we want to look at in geometry generally are circles and lines. And for inversion to be useful, we need it to kind of treat circles and lines nicely. If it turns out that like we invert a circle and it maps to some kind of horrible squiggle, then it's not going to be very much use to us. So we'd hope that inversion does nice things to circles and lines. And in fact, I claim that inversion maps circles and lines to circles and lines. But it's not quite as simple as mapping every circle to a circle and every line to a line. But when you start off with either a circle or a line, what you end up with is either a circle or a line. Does that sort of make sense?
Made sense to me. Should we write it down as a statement about?
Yeah. Okay. I'm going to move to like frame 2 if that's okay. It's a little bit more space.
Following you.
So, I guess a circle or a line will map under inversion to either a circle or a line.
So this is a statement about inverting every single point that's on your original line, inverting each one of those using that rule, OP times OP prime is R squared. And inverting all of them, and you end up with some squiggle that turns out to be either a straight line or a circle again. It's pretty cool.
Which is like not intuitively obvious, right? Like you'd have to think about it for a while to kind of even come up with this claim, but it's true and it's cool. So I guess the simplest case to deal with is if I have my circle omega and I have a point O, and then I draw a line through the center of omega, so line through O, I might call this L. It's quite easy to see what L will map to, because if you take some point P, by definition of inversion, we know that the image P prime lies on this line OP, which is L. So every point on L, when we invert it, will map to another point on L. And then kind of, as we vary P up and down L, we're going to actually end up getting to every single point on L because of this idea that like when you invert and then you invert again, you get back to where you started. So kind of, I know that P maps to P prime. So if I want to find a point that maps to P, well, that's just P prime, if that makes sense. And then again, worth noting, like as P approaches O, so then P prime's going to kind of move off to infinity in this direction. And then when P is actually at O, then we defined the image of O to be the point at infinity. So that's where this idea starts to come into play, that like the point at infinity lies on every line.
Oh, so because you've included the point at infinity, the inversion of this line L includes the origin. If you hadn't put that point at infinity in, it would have a kind of little gap at the origin, the missing point. Kind of including the infinity, the point at infinity is quite nice because it fills in that gap by mapping perfectly to the origin under inversion.
Yeah.
I can see that's quite nice.
Pretty nice.
Even if it took a sort of separate definition to make it work.
So I guess we've done lines through the center of inversion. So maybe the next kind of easy case to deal with would be circles through the center of inversion. And in fact, I'm going to prove that these map to not circles, but lines. So if I take my point O, which is the center of omega, and I draw a circle, oh, it doesn't go through O, that's better. And I'm going to call this circle gamma. And in fact, I'm going to prove that gamma maps to a straight line under inversion. So let's let the center of gamma be some point C. And let's draw the line OC in. And let's say that this intersects gamma again at some point A. And then I'm going to invert A in omega to get this point A prime. And then what I'm going to do is I'm going to pick some random point P on gamma, and I'm going to see where P maps to under the inversion. And in fact, I claim that P will lie on this line through A prime that's perpendicular to this line OA. But we'll get there in a minute. So if I draw OP and I end up with this point P prime, which I'm claiming that this angle here is 90 degrees, right? But I don't know that yet, so I won't draw it in because I don't want to assume something I'm trying to prove. Now, at this point, I think there's a sort of kind of separate useful fact about angles in inversion that we need to cover if we're going to prove this. So as a kind of quick aside, if we take 2 points A and B and we invert them, so it's going to go somewhere over here, B is going to go somewhere over here. I claim to you that the angle OAB is equal to the angle OB prime A prime. So OAB equals angle OB prime A prime. So to prove that, we're going to use similar triangles. So I guess taking what we know, we have this relation OA times OA prime equals R squared, and also OB times OB prime is R squared. Yeah.
Yep.
So then if I kind of rearrange this, I get that OA over OB equals OB prime over OA prime. So kind of drawing out these triangles, OAB and OB prime A prime, you can see that like the ratio of kind of, let's get some different colors. The ratio of this side to this side is the same as the ratio of this side to this side. And then because also this angle at O is common to both triangles, we must have these triangles are similar. And that's enough to prove this fact that those two red angles are the same, just by the fact that the triangles are similar and therefore all their angles must be the same.
That's really nice. Just big similar triangles. So you get an angle that matches up. And okay, so you're going to use this. I can sort of see that you're going to use this to convince me that the angle in your first picture, the angle at A prime, you're going to try and convince me that that's a right angle and that P prime lies exactly above A prime. There's a right angle going on in here. How are you going to do that? You're going to find a right angle somewhere else, aren't you?
Yeah, so kind of in the place of our A and B down here, we've got points A and P. So angle O P prime A prime equals angle O. No, sorry, angle O A prime P prime, that's better, equals angle O P A. So what we're actually trying to prove is the angle OPA is a right angle. But that they look familiar. So there's a theorem called Thales' theorem, which is kind of was often referred to at school as like the angle in a semicircle is 90 degrees, which tells you basically that if you have points A, B, and C on a circle where AC is a diameter, then this angle ABC is 90 degrees. So applying that here, we see the angle OPA is 90 degrees. Hence angle A prime P prime is 90 degrees. And so P does indeed lie on this line through A prime, perpendicular to OA.
And that's true wherever you put P on that semicircle. So the image of that semicircle is everything above A. And I guess the image of the bottom semicircle is everything below A prime, on that straight line. That's really good. That's using like GCSE level geometry facts, which all those circle theorems people learn at GCSE, and similar triangles as well, classics. Chat, I want chat to know. Somebody in chat said because angle in a semicircle, and I want to know that I want them to know that their chat message appeared slightly afterwards, but they probably posted it slightly before. You know, they were.
Perfect.
I guess they already know that. I want everyone else to know that anonymous person was slightly ahead of us.
Right.
That angle fact looks really powerful. Okay, so you've convinced me that if you have a line through the origin, that inverts to a line. If you have a circle through the origin, that inverts to a straight line. There's some other cases that I think you claimed about circles and lines inverting to each other.
Yeah, so if we don't pass through the origin, then we kind of need to consider those cases. But actually, the case where we have a line not through the origin can actually be quite easily tackled by just applying the case about a circle through the origin. Because of this fact that inversion, like when you invert and you invert again, you get back to where you started. So to see that, let's consider we have our circle omega, we have O, and then we have some line. And I guess by the way I've drawn it, you can sort of start to see the parallels with the diagram we had before. But yeah, so if I draw a perpendicular from O to the line, and now let's call this point of intersection A. If I now invert A to some point A prime, and I draw the circle with diameter O A prime, then suddenly we're back to the case before, because by kind of what we did before, we know that that circle with diameter O A prime, that maps to precisely the line that we just had under inversion by the case that we did before. And then because when you invert and invert again, you get back to where you started. If the circle maps to the line, then the line has to map to the circle.
That's really nice. Okay, but because inversion is its own inverse, that sounds mad to say. But yeah, lines and circles go between each other. That's pretty good. I want to address one thing in chat before I let you talk about circles going to circles, which I think is the case that's left over. Someone in chat wants an application, or what do you do with this as a mathematician or physicist? We're about to see that this can turn problems into other problems. This thing about switching between circles and lines, I work on bubbles, maybe I used to work on bubbles, that's more accurate. Having a lot of circles around and being able to convert that into a different problem, using some sort of clever maths trick to convert my problem into a different geometry problem, I can sort of see how that might be useful. So that instead of working with loads of circular bubbles around, I might be able to convert them into a collection of lines and circles. Switching between problems is quite a hard math skill to justify, because you never really know when switching from one problem to another problem will be helpful and when it won't. But hey, one of those things, I guess. Okay, that was for the two people in chat who wants to know about applications. Sorry, Rebekah, you were about to tell me about circles mapping to circles, I think.
Yeah, so if you have a circle that doesn't pass through the center of inversion, then that maps under inversion to another circle which also doesn't pass through the center of inversion. And I don't know whether we have time to prove this. It's doable, and it's doable using kind of similar methods and like GCSE circle theorems. It's a little bit more involved, the proof, but I wonder whether maybe it's worth moving on to some applications.
Should we leave it for our homework exercise? Do you want to draw a picture of a circle inverting to a circle, and we'll leave it as an exercise in GCSE? Hey, the person in chat is back and says thanks for answering the question. I just had to get a moment. I'm a very physicsy sort of person, so I can respect methods for the sake of methods, especially if I've got circular bubbles. Okay, so there's a circle that doesn't go through the origin, and maybe it inverts to some circle over there. I think it's... Yep. Yeah. Is it worth noting that as a result of that, the centre of the circle doesn't go to the centre of the other circle? I think that's the case.
Yeah, that's actually really important. So you kind of think that then if I put kind of P here, that then P prime would be here. But like, because inversion isn't distance preserving, like that isn't actually the case. And you can you can play around with that and you can see that that won't necessarily always hold. In fact, in most cases it doesn't hold.
If it was distance preserving, it would be easy, because you would follow the centre and then you would say the circle is all the points that are equal distance and they're preserved. That's not how it works, so it's slightly surprising that it ends up being a circle anyway. Oh, that's mad.
Yeah. Yeah, it's cool.
Okay, circles go to circles.
So shall we have a look at an application now?
Yeah, sure. An application to a geometry problem or something, right?
Yes.
Before that physics person in chat, who I respect because physics. Application to geometry first.
So this is like probably one of my favourite problems. I think I actually talked about it in my personal statement, which is kind of weird to think about. But over here, we've got what's called a Pappus chain. So basically, we've got 3 semicircles here. So one has diameter AB, one has diameter AC, and then one has diameter BC. So all the centers of these semicircles lie on this line. And it might be useful to just put the other halves of the circles in as well. And then we've got this kind of weird chain of like light blue circles, which is kind of mind-boggling to look at. So we have this first circle here. If I let kind of this circle here be like C1 and then this be C3 and C2, then this circle here is like tangent to all 3. And I'm going to call this lowercase omega 1. I hope that's not going to be too confusing. And then we've kind of kept going. So this lowercase omega 2 is like tangent to C1 over here, and it's tangent to C3 over here, and then it's also tangent to omega 1 next to it. And then we have omega 3 over here that's kind of constructed in the same way. And then we just keep going. It's kind of infinite chain of smaller and smaller circles, which is quite a aesthetically pleasing diagram, I think.
It's quite natural, I think. You started off with some circles that were tangent to each other and then just filled in a chain of circles, making them tangent to, I guess, these are like the biggest bubbles that you could fit in if you're a bubble scientist or something. A chain of circles going through there. Okay. You got it.
I guess mathematically though, it's a bit of a nightmare because, like, it's just very difficult to deal with all these tangency conditions. And the problem we're going to consider is I'm going to let the radius of omega n for each n be Rn. And then what I'm going to be interested in is the distances from the centers of each of the omega n's to this line AC. So I'm going to let this distance here, this perpendicular distance, be D1. And then this can be D2, and so on. And then our question is, like, what is dn for each n? And in particular, can you find it in terms of the Rns? Because obviously we don't have any lengths here, so we can't get an absolute numerical value, but we can do it in terms of the other lengths in the diagram. And in particular, it turns out that each dn has a really nice kind of formula in terms of the corresponding Rn, which we're going to look at a little bit.
So there's some sort of... Yeah. Oh, sorry, carry on. There's some sort of relationship between the radius and the height that you get at the of each circle. And I really don't want us to go and solve all the quadratic equations for those. You call them tangency conditions. I guess it's when 2 circles are tangent, you could write down the quadratic equations for the circles, set them equal to each other, and I just don't want to write down that many quadratic equations.
Yeah, like if you tried to deal with this algebraically, I think it would just be a mess. And like, unsurprisingly, we're going to use inversion, and we're going to use inversion to turn this into a problem that's less of a mess. So I guess, first of all, we don't like that this chain of circles is tangent to these kind of 2 circles, C1 and C3. Like, that's just giving us a headache. And it would be much nicer if those circles were instead straight lines. Because if I have a bunch of circles and they're all tangent to a line, like, that immediately makes them easier to deal with. So we kind of touched on the fact before that, like, inversion lets you turn circles into lines under very specific circumstances. So in particular, if you invert a circle that passes through the center of inversion, then you're going to get a line. So we want to do an inversion where the center of inversion lies on C1 and C3 in order to map C1 and C3 to straight lines. And so the only point that lies on C1 and C3 is A. So it kind of makes sense that we might consider an inversion centered at A. And we don't quite know yet like what circle we're going to invert with respect to. We could do like a tiny little one or a big one. Essentially, you're going to get variations on the same kind of diagram. So just to kind of explore what happens, shall we just pick a random circle and do it and see what happens?
I like this. We're using the tool from before. Sorry to repeat it back, but you're using the tool from before. You're going to invert. We're not sure which circle, but something nice is going to happen to that diagram if you invert all of the many circles, because of what you've said about inverting particular circles and lines.
Yeah. So I guess let's look at where C1 and C3 map first. So we said before they pass through the center of inversion, which is A. I'm going to let my circle of inversion be uppercase omega. And I'm going to, if I look here, so C3 intersects uppercase omega at these 2 points. And so if we know that C3 maps to a line, that's got to be the line joining these 2 points, right? And that's not a very good line, but you get the gist. And then we can do the exact same for C1. So that intersects here and here. So like the image of C1 is this line here, and the image of C3 is this line here. Now, they don't look like lines at all, but if we assumed that I'd drawn them better than they did, you might start to think that those lines looked parallel. And actually,
should we switch to my Desmos thing?
Yeah, sure.
Might we switch to the Desmos thing? I think we switch to the Desmos thing. Give me a second. It's more slick. There we go. Okay, I've got a Desmos thing. So I got my circles. I draw in the circles. I'll come on Desmos, so you can do it. And then if you invert, you get these lines and this stack of circles. I guess is what you're about to invert.
Yeah. So those lines look a lot more parallel than my lines. I guess we haven't quite proven that they're parallel, but it's not too easy, it's not too difficult to do. For example, you can see that like C1 and C3, the only point at which they intersect is that point A that was our center of inversion. And so the only point at which the images can intersect is the image of A. And we know that that maps off to the point at infinity. So our two lines don't intersect anywhere in like the normal plane we can see. And so they have to be parallel. And also it's not too hard to show that like these lines are perpendicular to the kind of horizontal line AC, which again you can see kind of nicely from the Desmos. These lines become vertical lines. And kind of even more nicely, each of our circles in the Pappus chain, it's tangent to C1 and it's tangent to C3. So it has to be tangent to both of the images of C1 and C3, which are lines. So this Pappus chain ends up mapping to this kind of nice chain of circles that they all line up nicely between the lines, and they're all tangent to each other, and they're all congruent. So they're all the same size, which makes them a lot easier to deal with.
I stand no chance at drawing. I think it's about 40 circles on the red chain. If they were just random circles, I stand no chance of putting those into Desmos. But because they're all the same size and in a stack in Desmos, I like how to do that in Desmos. So it's a case of inverting that really pretty picture with the blue circles. Under inversion, it turns into just parallel straight lines with a stack of circles between them. Yeah, so parallel lines only meet at infinity, says Miles in chat, which starts to make the point at infinity feel like a good construct as well, because that, I think you said it before, it's that point where parallel lines, any pair of lines meet at the point of infinity. It just kind of ties things together a little bit. I will share the link for the Desmos if I can work out how. Do you want to switch back to the Miro boards, or do you want to stay on the Desmos? Up to you.
Let's have a little kind of switch back to Miro for a bit, and then we can come back to see how we use the Desmos to finish the problem.
Sure.
Okay, so I guess we have a slight issue at the moment in that, okay, we've done our inversion. I guess this circle C2 over here, like it passes through B and C, and kind of B prime has to be here and C prime has to be here, just because of the way things intersect. And so this circle goes to here, and then we construct our chain like this. But we've lost some information in that I now don't know anything about the radii of the inverted circles. Like, I'm supposed to be working some distances out in terms of the RNs, but like, I don't know how these circles relate to any of the RNs at all, which is kind of a problem. And we don't know how like the distances of the centers of these inverted circles from the line AC relate to the DNs at all. So we've got a problem. And there's sort of like a proposition or kind of a fact about inversion that I'd like to show you that will hopefully help us to solve that problem a little bit. So I'd like to kind of introduce a definition. So we say that two circles are orthogonal if, when I draw the tangents to the two circles at their point of intersection, these tangents meet at 90 degrees. So it's kind of a fancy way of saying that the circles themselves are almost like perpendicular to each other. And the reason that I've introduced this is that it turns out that if you have a circle which is orthogonal to your circle of inversion, so I have some like gamma over here, and then this is omega and this is gamma. If I invert some point P on gamma, then it maps to some point P prime, which is also on gamma. And so like gamma maps to itself, which is quite nice. Do we have time to prove this, or do we want to just take it as read?
I'm trying to stay on mute because there's a load of background noise in my place. Is it true, because you already proved that angles under inversion do a nice thing?
Yeah, that would probably be, although the proof I know that angles do nice things, I think relies on this fact. So it might be a bit of a circular argument, but
chat would like some proof. Let's do a proof.
Chat would like proof. Okay, cool. Right, okay. So let's assume we've got this circle gamma, it's orthogonal to our circle of inversion. Let's assume that gamma and omega meet at some point t. And what I'm going to do is I'm going to draw the tangent to gamma at t. Now we know, because the circles are orthogonal, that this tangent is perpendicular to the tangent to omega at t. And so a line that's perpendicular to a tangent must be a radius, right? So this line, this tangent line here, actually passes through O, where O is the center of omega. So hopefully that makes sense. So at this point, I'm going to introduce a point P, say here. I'm going to draw OP, I'm going to extend it. I'm going to have this point Q over here. And what I'm claiming is that P inverts to Q, right? So it turns out we can use, well, we can draw this triangle PTQ. And then I'm going to use the alternate segment theorem, which I don't know whether people know. It should, again, it's one of these kind of GCSE things. But basically that says if you have a triangle like ABC in a circle like this, and you draw the tangent at C, then it tells you that like this angle equals this angle, and this angle equals this angle. So applying that to triangle PTQ, we get that this angle equals this angle. And then if I look at triangles OTP and OTQ, I'm going to get some similarity. So OTQ and like OTP. Then like, so OTP was this angle, OQT was that angle. And again, we've got this shared angle at O. So like this angle and this angle are the same. So now we have similar triangles, and we can essentially do like the length relation thing. So we go, okay, kind of comparing corresponding sides. So OT over here corresponds to OP over here. And then that ratio is the same as if you compare OQ to OT. And then you multiply up OT squared equals OP times OQ. And then the last thing to notice is that OT is the radius. So then you get OP times OQ equals R squared. And so Q must be the inverse of P, which is quite nice. Cool, okay. So kind of applying that back to our original problem, we now have that like circles orthogonal to the circle of inversion map to themselves. So let's just like clear this diagram for a sec. Okay.
I love that you use the alternate segment theorem. That's one of the GCSE theorems that people sometimes ask me, what's the point of this one? And here it is, in a nice problem.
That's the point.
Orthogonal circles are self-inverse under inversion in a circle. There you go. Something clever to say when people ask you what the alternate segment theorem is used for. That's brilliant, Rebekah. Okay, back to this problem. I've zoomed in on Papa's chain again.
Cool, okay. So let's say, for now, let's just focus on like omega-3, for example. And we're interested in finding D3. So wouldn't it be nice if we could do an inversion that fixed omega-3? Because then in our kind of new inverted image, we'd know stuff about R3 because like we have omega-3, it's the same. And we'd know stuff about D3 because like omega-3's position hasn't changed. So can we do that? Well, if we draw a tangent from A to omega-3, and then we let the point of tangency be like T, and then we draw a circle centered at A that passes through T, well, I think you can probably convince yourself that that circle will be orthogonal to omega-3. So like, yeah, you've got a radius here, and like this radius here is perpendicular to the tangent to the circle, which is also like perpendicular to the radius, which is itself a tangent of omega-3. It's quite sort of, if you fiddle around with it, you can see.
Is it circular logic? No, I'm sorry, that was uncalled for. So things go, you can choose this circle of inversion really carefully so that omega-3 is orthogonal to that circle of inversion.
Yeah, and then omega-3 will stay fixed. But all the logic we had before about like, oh, we're going to get a chain between parallel lines, that still holds. So if we remember, we said that this circle C2, we said that like, if we let this point here be like B prime, this is C prime, we said that C2 had to map to this circle here. So it sort of got symmetry in the line AC because B maps to B prime, C maps to C prime, and we've got this tangent C. We know that omega-3 maps to itself because we constructed our circle of inversion that way. So then we've got to fit omega-1 and omega-2 in here. And so they've got to, like, they're just forced to be like that. That's supposed to be tangent. And so now we're in a position where, quite literally, if we want to find D3, which is quite hard to see on the diagram, but this distance here, all we have to do is literally count the radii. So as we go along, we have one radius here. I don't know if that shows up. Yeah. And then two more radii here, two here, and two here. So all in all, D3 is just 6 lots of R3. Oh, I don't know if that shows up. There we go. And more generally, you can apply that to omega n for any n, and you'll get that dn is just 2n Rn, which is surprisingly simple and quite satisfying.
It's mad that there's that relationship between the distances up and the radius and the radii. You haven't needed to solve for what the radii actually are or where the positions are.
No.
The inversion is so carefully chosen for this, so that you choose the inversion so that one of the circles omega-3 stays still, and then the rest just stack together because the inverted problem is so pretty and just a chain of circles stacked together. I think we can flip back to the Desmos quickly because the Desmos Desmos has been set up to do this. I'm hoping people didn't notice that mysteriously one of the circles in the Desmos thing matched up between the blue and the red. And that means that if I choose the circle if I choose the radius of inversion just right, I'm not sure I can get this to work. There we go, that looks pretty good. This looks like a version of your picture now, where that first circle maps over here, and then just count the radii to work out how high that one is. It's just lovely that I don't know. This is a bit of a stupid thing to say, but the fact that that blue circle is the same as the red circle feels a bit like its own mirror image. So this fact about the kind of mirror world, the nice red lines in the mirror world, actually starts saying something about the real world with the blue circles. The kind of the mirror world helps us out. So it's really pretty. Chat is very impressed, I think, and I think it is now okay for me to share the Desmos thing with chat. Let's stick that in chat now. There we go. So link in chat, and we'll go into further reading and stuff. If you want to, if I get around to typing up the further reading, for more Desmos fun messing around with circles. Cool, that was really nice. That was such a good proof.
Is there time to talk a little bit about Steiners Poorism, or?
Yeah, we've got about 9 minutes. So I'm not sure we can prove things about it, but we can maybe show it. Definitely state it.
Okay, 9 minutes. How far can we get?
9 minutes.
So another really cool problem that can be solved using inversion is a statement called Steiners Poorism. So it turns out, like, I had to sort of look this up, but a poorism is a like kind of weird, outdated maths word for a statement which is either false or true in infinitely many cases. So it sort of never gets used, but like Steiners Poorism is a poorism. And hopefully you'll see why in a minute.
P-O-R-I-S-M, poorism, word of the day.
That's one to like take into maths classrooms and confuse teachers with. Okay, so the setup for Steiners Poorism is as follows. So if I'm given like two sort of bounding circles, I'm going to call them, so these two black circles, I hope you'll agree that I can draw some kind of red circle that's like tangent to both of them. And actually, like, there are lots of different places I could put this. I could like do one over here. There are sort of infinitely many choices of red circle. But once I've got my red circle, I can draw. So this is looking very similar, starting to look similar to the Pappus chain. So I'm drawing a blue circle here, which is tangent to the two bounding circles and also to my red circle. And then I can do the same and just carry on, basically. This is actually really, really hard to draw. Yeah, so we keep going. And now we've got to, let's make that a bit better. We've got to a point here where, like, our next circle, it needs to be tangent to this blue circle and to the bounding circles. But the question is, will it be tangent to the red circle or not? Like, do we get back to where we started in a nice way and form this kind of what's called a closed Steiner chain? Or do we end up with some horrible mess, which we probably do, where like they intersect and it's kind of not pretty. So okay, here, like, we don't get a nice closed Steiner chain. So maybe I get rid of all my circles and start again. So like, maybe I just picked a bad red circle, right? Maybe if I start like here, then I'll be able to get all the way around. Maybe I just picked a bad red circle. And what Steiners Poorism says is basically like, no, if you give me the bounding circles, then it doesn't matter where I put the red circle. So either I can put the red circle wherever I like, and I'll always get this nice, pretty closed Steiner chain. Or it doesn't matter where I try to put my red circle, I will never get a nice closed Steiner chain. Which is a cool fact, and like, it's not obvious, but the way you solve it is with inversion.
I wonder if
And I guess like,
we've got 2 minutes before. I'm
okay,
worried you might tell them the inversion. I think we've got just enough time for chat to maybe come through and guess what the inversion is,
okay.
or do you want to do it like that? Or
Yeah, I mean, it's really difficult to construct the actual inversion, but like
ah,
it's easy to explain like what the properties of the inversion would have to be. So there's a sort of really easy case where like if your circles have the same center, then like it's really obvious that it doesn't matter where I put the red circle because there's sort of rotational symmetry. So like wherever I put that circle, I'm either going to end up with a nice chain or I'm not. So the key is, and it's really hard to like construct the inversion that makes it happen, but the key is if you can do an inversion that maps your two bounding circles you're given to a pair of concentric circles, then that basically tells you that it doesn't matter where you put the red circle. Because if it doesn't matter where you put the red circle over here, then like it clearly doesn't matter where you put the red circle over here. And like what Steiner showed is there does always exist an inversion that kind of given these two starting bounding circles, that one inside the other, they don't intersect, that you can always get them by inversion to a pair of concentric circles.
right. Okay, I shouldn't have set it as a challenge for chat in under 5 minutes because it's hard, but I can sort of see that. To me, if once you've accepted the point at infinity, the Pappus chain that you showed us before, with that arching band of infinitely many circles disappearing off to the point twinkling at infinity, that kind of reminds me of it. It looks a little bit like a distorted version of a big stack of circles. And I guess this looks like a distorted version of the symmetric picture as well. That's not a proof, that's just me saying, oh, it seems likely that maybe you could distort one of these things into the other. Maybe with an inversion, I guess. So Steiner's contribution of actually finding the inversions or proving that they exist. Could you say the rotational symmetry bit again, just to explain what happens when you do the rotational symmetry and keep inverting everything?
Okay, so like it doesn't matter where I put the red circle over here because like I can rotate my diagram to move any, like wherever I put it, I can just rotate it and you can see that like whether or not I can construct a chain around here depends only on like the respective radii of the bounding circles and not where I put the red circle. But then basically like if I construct or I start to construct this chain around here, then when I invert it, because of like all the tangency conditions and because inversion kind of preserves this tangency, it's going to map to a chain like this around here. So if I change where this red circle is, it's just going to change where it maps to. So it'll map to some other red circle. And we know that it doesn't matter where this red circle is. So therefore it can't have mattered where I put this red circle. I get the same result either way, because if I get a closed chain in this kind of original plane, then I will get a closed chain over here by the fact that inversion preserves tangency. I hope that makes sense.
That was quite nice. I found a GIF. So you sent me some GIFs before of this when we were discussing the topic. Rebekah sent me some GIFs. I haven't found the GIF that you sent me. I found a different GIF, but I'll show the GIF of the Steiners Poorism thing happening. Sorry, it's not the one that you sent me.
That's all right.
So nice. Here it's going. Okay. So what we're looking at here is it 7 circles? And before inversion, they're equally spaced around the inner circle. And then inversion happens, and it maps circles to circles, and you get this nice chain of circles going round and round. Yeah, pretty good stuff. Okay, we're getting close to 6 o'clock, so I think we're going to leave it there. We've convinced the physicist in chat has said pretty sweet, so we've shown something that the physicist... I count that as a success. Chat really liked your proof we're using the alternate angles thing about orthogonal circles mapping to themselves.
Awesome.
I think I'm going to try... I've missed a couple of weeks, but I'm going to try really hard to put together further reading for this, because there's other gifts that we haven't shown people, and I think was there another geometry problem you wanted to do?
Yeah, so I don't know if anyone's heard of Ptolemy's theorem, which is kind of like, it's essentially a circle theorem, but it's a little bit more complicated than the GCC ones. And it talks about like lengths between like 4 points on a circle. And actually you can do a really nice inversion that turns the setup of Ptolemy's theorem into something really simple, and then that provides a really nice proof of Ptolemy's theorem. And there's a really nice number file video on it as well, you can watch.
I've seen a couple of related number file videos. Miles wants further reading. I think that's a request. As soon as I've mentioned further reading, I have to do it. So check back either tomorrow or over the weekend or Monday or something for more links and other resources on geometric inversion. Say thank you to Joe moderating chat. Thank you, Joe, for keeping chat running. Thanks everyone who joined in with chat. The researcher this week was Rebekah. The presenter this week was Rebekah. It sometimes comes back. We lost it right at the end. We were just saying goodbye. The researcher this week was Rebekah.
Sorry.
The presenter was Rebekah. Thanks to Joe in chat. Thank you very much to all of the technology for working for a full hour before it broke. This has been the Oxford Online Maths Club. We do this every week. We'll see you in 167 hours for another episode of the Oxford Online Maths Club. Take care. Bye.